Look at your hands or the table in front of you. They feel perfectly solid, but that solidity is a highly convincing illusion. If you were to take a single atom and enlarge it so its nucleus was the size of a dot resting on the 50-yard line of a massive football stadium, the closest electrons would be buzzing around way up in the highest grandstands. Everything in between is just empty space. Look closely at that tiny central nucleus, and you'll find protons and neutrons. Inside those are even smaller, vibrating grains of matter called quarks. Invisible forces provide the scaffolding for this void. The strong nuclear force acts as a universal glue locking the quarks together, while electromagnetism keeps the distant electrons tethered to the center. Every physical object you interact with is a complex manifestation of these tiny, space-filled building blocks holding firmly onto one another. For centuries, humans worked to catalog the variations of these atomic structures. This effort culminated with chemists like Dmitry Mendeleev, who organized the known building blocks of reality into the periodic table of elements. We learned that the lightest elements were forged in the intense heat of the early universe, while heavier ones, like iron and carbon, were cooked inside the cores of dying stars. Yet, despite this comprehensive map of the physical world, our standard model of physics contains a glaring omission. This pie chart shows the total composition of our universe. That tiny illuminated sliver represents all the ordinary matter we just discussed. Every star, planet, galaxy, and human combined accounts for roughly 5% of the cosmos. Our entire map of physics describes only the glowing icing on a massive, unseen cake. In the 1970s, astronomers started tracking the outer edges of distant galaxies to see exactly how fast they were spinning. They found a major problem. Based on the amount of visible starlight and ordinary mass inside these galaxies, they were spinning far too fast. According to standard gravitational math, they should instantly fly apart and scatter into deep space. Look at this bar chart overlaid on the surviving galaxy. To keep a structure this large intact at those rotation speeds, there has to be 5 to 7 times more mass present than what we can see, acting as an invisible gravitational glue. Scientists call this missing mass dark matter. We can measure exactly how much it weighs, and we can observe how its gravity bends light, but we have absolutely no idea what kind of particle actually creates it. This invisible ghost grip is the primary architectural support of the cosmos. Without it, our galaxy and our solar system could never have formed. Our calculations regarding the early universe present another massive discrepancy. According to the math of the Big Bang, every time a particle of ordinary matter was created, an exact twin, a particle of antimatter, should have been generated right alongside it. These twins have a violently incompatible relationship. The moment matter and antimatter touch, they annihilate each other completely, converting their mass into a pure flash of energy. If the universe truly started with perfectly equal amounts of both, they should have canceled each other out immediately, leaving behind a cosmos filled with radiation and absolutely nothing else. Yet we look out into the night sky and see a universe packed with surviving matter. We don't know where the antimatter went, or why a slight imbalance favored the material we are made of. Our very existence defies the initial math. We are the leftover debris of an ancient cosmic annihilation event that we still cannot explain. To find out why matter survived at all, physicists try rewinding the expansion of the universe backward to its absolute origin, building on the early hypotheses of expanding space proposed by Georges Lemaitre. But as the clock runs backward and the universe becomes infinitely small, hot, and dense, our two most reliable physics rulebooks, general relativity, which governs gravity, and quantum mechanics, which governs particles, begin to contradict one another completely. This timeline illustrates our limit. As we rewind toward the 13.8 billion year mark, our equations smash into a mathematical boundary known as the Planck wall. Before this fraction of a microsecond, our current understanding of physics stops working entirely. Because we cannot see past this wall, some physicists suggest the Big Bang might not have been a sudden appearance from nothingness, but rather a cosmic bounce originating from an older, contracting universe that simply compressed and rebounded. The origin of matter remains shielded by the fundamental limits of human mathematics. Scientists are building massive engineering projects to pierce through the darkness of the unknown. Inside immense particle accelerators like this one, engineers are manually colliding particles to fabricate and trap fleeting, microscopic amounts of lab-made antimatter so we can finally study its properties in a lab. We are also harnessing muons, heavy, unstable cousins of the electron created by cosmic rays, to safely peer through solid rock and map hidden voids inside structures as dense as the pyramids of Giza. And stationed 1 million miles from Earth, the James Webb Space Telescope uses massive golden mirrors to capture infrared light, specifically designed to watch the very first stars igniting shortly after the Big Bang. We have progressed from ancient philosophers guessing at the nature of dust to engineers building planetary-scale tools to catch invisible forces. Modern physics is now venturing into a region where our most basic assumptions are being tested. While our bodies are built from stardust, that material represents only a luminous 5% anomaly floating within a vast ocean of the unknown. The ultimate destiny of our universe, whether it expands forever or eventually collapses, relies entirely on mapping those missing dark pieces. To truly understand reality, we must stop looking only at the light and finally learn how to read the shadows.